Okay, so before we move on, I want to talk about quickly indirect proofs. So there are actually many ways to prove indirectly, and I will show you some examples. So maybe for the beginners, the contrapositive is easier to understand. So what it means for contrapositive is that it's called proof by contrapositive. So if you want to show that P implies Q, then all you need to show is not Q implies not P. I didn't introduce the notation not because I think it might be too simple, but this symbol just means not. Okay, so not P, it is not P. So if P is true, then not P is false. And if P is false, then not P is true. So to show P implies Q, all we need to show is not Q implies not P. Or in the other way around. So if we want to show not Q implies not P, all we need to show is P implies Q. Which means the essence of this is P implies Q is true if and only if not is true. Okay, so P implies Q is true if and only if not Q implies not P is true. So you can just check it in many different ways. So you can see they're actually, so as long as you can show this implies this, then you can just switch the variable to show the other way. So we just so let's just prove for this direction. Okay, so how will we prove this? So I have to assume this as the assumption. So pay attention, we're not assuming P or Q, we're assuming P implies Q. Okay, we're assuming this statement is true, and then we are asked to show that not Q implies not P. Okay, and since we are asked to show something implies something, we have to assume this is true. So let's assume that not Q is true. So what we want to show is not P. And then we can use the idea of proof by contradiction. Since we know that either P is true or not P is true, and we want to show not P is true, what we can do is that we can assume P is actually true, and we can deduce some contradiction, so that P cannot be true. If P cannot be true, then P has to be false. Does that make sense? In order to show P is false, we can assume by contradiction that P is not false or P is true. So if P is true, then because we have assumed P implies Q, then this will mean Q is true because P implies Q. Because we have P implies Q and also we have P. So then by modus ponens, we have Q. But we have assumed Q is false. So this will cause a contradiction. And then this is denoted by this symbol. This means contradiction. Which means P cannot be true. Does it make sense? Because if P is true, then by the assumption that P implies Q, we have Q. But also we have assumed not Q, which means this will lead to a contradiction. The problem with the contradiction is that P cannot be true, so P is false. So this is an example of proof by contradiction. So which means you can see that any proof of contrapositive actually contains a proof by contradiction. So we have to talk about proof by contradiction, which is super powerful and useful, and many beginners are not good at it. So if you understand the main idea, then you feel very confident. So let's take a look. So in order to show that P is true, what you can show is that P cannot be false. Okay, so you can assume by contrapositive, or you can indicate at the beginning that you are proving by contradiction. So you can say prove by contradiction. So then you can assume the negation of the statement. So you can assume P is false, and then after some calculations or some logical manipulations, in the end, you deduce a contradiction. A contradiction is something that it means that something cannot happen. It means this will lead to a problem. For example, you deduce 1 is bigger than 1, which cannot be true. So this is a contradiction. So contradiction is something that cannot be true. So if you assume not P and deduce a contradiction, it means P cannot be false. But now you know that by some axiom, every statement has to be true or false, and it cannot be false, so it has to be true. So this concludes the proof. So this idea is called proof by contradiction. And what we have shown here is that actually every contrapositive statement can be proved by contradiction, which means this is a better method than the proof by contrapositive. And you can see that if you want to show proof by contrapositive, it has to be in the form of P implies Q, right? It has to be in this form, and then you change Q to here and then add a not, and you change P to here and add a not. So this is in a very special form. It's in the form of something implies something, but this proof by contradiction can be applied in any statement, right? Because this is any statement P. So one of the most famous examples in history of math is that one can prove square root of 2 is not rational. Maybe I can just maybe I can just prove it quickly. So to prove it, the only known method is probably just by contradiction. So this Q is the set of rational numbers, rationals, and by definition, it is the set of all P over Q, where Q is let's say n star or n1 is a positive integer, and then P is an integer, and then they are co-prime, or the GCD of P and Q, or the greatest common divisor of P and Q is equal to 1, or they are co-prime. Okay, so let's assume by contradiction. So this is something we want to show. We want to show square root of 2 is irrational. So if square root of 2 is rational, then we want to deduce a contradiction. So then we can write square root 2 as P over Q, where PQ are things over here. And because this is positive, so we can assume PQ are all positive integers, such that the GCD of them is 1. So then they are co-prime. They don't have any common prime divisor. So then we can take, by definition, the square root of 2 is the number that when you take square, it becomes 2. So you can take square of both sides, then you get 2e is equal to p squared over q squared. So then p squared is going to be 2 times q squared. And now, if you look at this expression, then you realize, so here p and q are both integers. So p squared is 2 times some integer, which means p squared is an even number. right? Because it's a multiple of 2, so it's an even number. And then I claim that P has to be even as well. So if P is, so we can prove this by contradiction. So if P is odd, then you take the square of an odd number, it's still odd, right? Because for example, 1 squared is 1, 3 squared is 3. So the square of any odd number is odd. But here, P squared is even, so this is false, which means P cannot be odd. So you prove that P is even, okay? So this is like a quick claim and a proof of the claim. Proof of the claim. So which means, so this tells us that P is even. So if P is even, then you can write P as 2 times R, for example, where R is also a positive integer. Then this becomes 2, because we have P squared is equal to 2 times Q squared. So 2R squared, which is 4 times R squared, is equal to 2 times Q squared. So then we can cancel out 2 to deduce that 2 times R squared is equal to Q squared. But now, if you look at this expression, then Q squared becomes an even number. Becomes an even number. Because it is a multiple of 2, right? Q squared is even. And then by exactly the same argument as here, you can show that Q is also even. Which means, if you look at the original expression, you assume that PQ are co-prime. You can always do it if it is a rational number. Then you can cancel out all the common multiples and make them co-prime. But you can see you have shown that P is even and also Q is even, which means 2 will divide P and Q, which means the greatest common divisor will be at least 2, and actually a multiple of 2 if you have learned some number theory. So this cannot be true. So this will lead to a contradiction, which means, so the contradiction is that you can always assume that PQ are coprime, but you can show that they cannot be coprime. They will have a common multiple, which is 2, for all the pairs PQ. Even when the GCD should be 1, you can deduce the GCD is bigger than 1. So this is a contradiction, which means it cannot be rational. Okay. So I think the importance of proof by contradiction is that you should always keep it in mind. So whenever you cannot prove something directly, you can assume it is false and see what happens. So I think this idea is quite important. And I think I still have some time for this video, so I'll talk quickly on the proof by induction. It's not hard at all, but one has to know it. So let me also talk about the proof by induction. So this only works for statements over, let's say, over integers. So the importance of the integers is that they are discrete, right? Maybe you start from 0, 1, 2, 3, etc. It cannot be over all the real numbers. So I will explain what I mean. Or it actually works over all the, let's say, over all the n, m, which are the numbers from m to infinity. So m plus 1, m plus 2. And when I say to infinity, I don't mean that we have a number that is infinity, although we can actually define it in a rigorous way, but let's just forget about it for now. It means it's just all the natural numbers bigger than or equal to m. We denote it by nm. So let me tell you about the induction. So let's say we want to show. So first, let's say we have. So for each n in the natural numbers. So let's say we have assigned a statement, which can be true or false. But in the end, we want them to be true for all n. Pn, which means P1 is a statement, P2, so let's say we start from P0, so all of them are statements, and we want to show that all of them are true. Pn is true for all n, and just in the next video I will say we can denote this by this symbol. This means for all. So in the next video I will say I can write this as for all n in n we have Pn. So we want to show this is true, and to prove this we can use proof by induction. You can say proof by induction. So it means you first prove the first one is true. So in this case, the first one is P0. If it starts from 1, then you just prove P1. If it starts with Pm, then you just prove Pm. You just prove the first case. Okay? So you can call it the base case. So the base case is just you want to show that in our case P0 is true. So just proof blah blah blah, and then in the end you get P0 is true. Okay, you're happy, and then you want to do the induction, or let's say the induction step. So all you need to show is that if the previous one is correct, then you can deduce the next one. Then you can see, because you have shown the first one is correct, and then each like implication is correct. So then you can use the first one implies the second one to deduce that second one is correct, and then the second one implies the third one to deduce that the third one is correct, and so that you can show everyone is correct, right? So which means all you need to show is that you want to show for all n, in our case for all natural numbers, Pn implies Pn plus 1, right? Or in the next video, I would denote this by for all n in n. Pn implies Pn plus 1, which means the previous one implies the next one. And to prove it, all you need to do is that you just fix any n in the natural numbers. This n is just a variable, okay? It represents some or any natural number. And then what you assume is that you assume this statement is true for any Pn over here. And then you want to show that Pn plus 1 is true. Which means now you assume Pn is true, and then all you need to do is to prove that P of n plus 1 is true. So let me show you an example. So first, I think it makes sense, right? So whenever you want to prove by induction of some statements over n, you can only prove it over n, or n1, or nm. You cannot prove it over real numbers, okay? So for example, if you have a statement over all the real numbers, you cannot prove it, okay? You cannot prove it by induction. So you just separate into two parts. So first you show the base case is correct, and then you show the induction is correct, which means you use the previous one to deduce the next one. So let me show you an example. So let me just do the simple one. So I want to show that for all n bigger than or equal to 1, we have, so let me just denote by this notation. For all n in n star, we have 1 plus 2 plus up to n is equal to n times n plus 1 over 2. Okay, how do we show it? So first, the base case is that if n is 1, then we evaluate both sides. Then the left hand side, the left hand side is simply one term, which is 1. And the right hand side is 1 times 1 plus 1, which is 2, divided by 2, which is 1. So both sides coincide, so this means this is true for the base case. Okay, and now let's do the induction step. So I want to show that if this is true for n, then this is true for n plus 1. So which means we can assume that this is true. 1 plus 2 plus up to n is n times n plus 1 over 2. And we want to show that if we do this to all the way to n plus 1, then then this should be also true. Like this statement should also be true for n plus 1, which means for the left hand side, the last term is n plus 1, right? And here we have to plug in the value n plus 1 into n. So then this becomes n plus 1 times n plus 2 over 2. So all we need to show is this is correct. And by induction we can, so this is called the induction hypothesis. Induction hypothesis. So we can assume the induction hypothesis is true and we have to use it. If we don't use the induction hypothesis, it's not proved by induction. So here, this is something that we can use, or some assumption, or some hypothesis. So this is called the induction hypothesis. Okay, and by induction hypothesis here, we know that we can evaluate all the previous terms by n times n plus 1 over 2. So if we add them up, then you can say, to show this is equal to this plus n plus 1. And then you can factor out as n plus 1, so then you get maybe n plus 1 over 2. So this becomes something plus 2, which is n plus 2, and you win. This is n plus 1 times n plus 2 over 2. This is simply some algebra. So you can prove this for any n, for any statement. So first, by induction, you have proved this is true. And you can show that, for example, this is just by coincidence, okay? You can show that for all n, if you add up all the cubes of them, so 1 cube plus 2 cube plus all the way to n cube, then this is going to be simply the square of the previous term, which is n times n plus 1 over 2 squared, which is n squared n plus 1 squared over 4. And one might be interested why this is true. And I can tell you this is totally by coincidence. And the reason why I can tell you is because if you can actually find the formula for all the 1 to the power of m, to the power of m, up to n to the power of m. And this is related to the Bernoulli numbers. I think it's called Bernoulli numbers, like Bm, Bk. It's related to the Bk's. And if you just evaluate just some of them, then you can notice that you cannot find any pattern like this anymore. So this is the only like exceptional case, which is quite amazing. So let's just forget about the pattern here. Let's just prove for this statement. So the base case. So if n is 1, then the left hand side is 1 cubed, which is 1. The right hand side is equal to 1 squared 2 squared over 4, which is 1. Okay, it has to be true. Okay, and the induction step, you assume it is true for n, so you assume that this is true. So you assume 1 cubed plus all the way to n cubed is n times n squared n plus 1 squared over 4, and you want to show that if you have an additional term, which is n plus 1 cubed, then it should be n plus 1 squared n plus 2 squared over 4, right? And to prove it, you can use the induction hypothesis to evaluate the first n terms. So then this would be, if you add them up, then all the previous terms is actually n squared n plus 1 squared over 4 with n plus 1 cubed. So you can write this as n plus 1 squared times n plus 1, because so then you can factor out n plus 1 squared over 4, right? You can think of this as you divide by 4 and then, so you can think of this as you divide by 4 and then multiply by 4. So then this will be n plus 1 squared over 4 times n squared plus 4 times n plus 1. And then this is n squared plus 4n plus 4, which is n plus 2 squared. So then this becomes n plus 1 squared, n plus 2 squared, divided by 4, and you win. So you cannot find any pattern like this anymore in the higher dimensions, because you can prove you cannot find it, as I said, because the real formula related to this is Bernoulli numbers. And just don't try. Here it should be, we should have a square. Just don't try to prove anything by your own. You cannot. Maybe if you're interested, you can just look at the Bernoulli numbers and see why you will have this relationship. Okay, so these are all not hard examples, and in practice we can have much more complicated examples, and all we need to know is why it's not why they are true, but how we can use them. So if we're asked to prove a statement like prove by induction, then we have to know how to write the proof. So for example, if we I think I have missed the example of proof by contrapositive. So this is an example of proving by contrapositive. So now let's assume that x is a real number. So now I ask you to prove that if x squared minus 5 squared plus 6 is not equal to 0, then x is not equal to 2. Okay? So how can we prove this? So what you can prove is that you can say prove by contrapositive. All you need to show is that you can change this problem into the problem of x equals 2 implies x squared minus 5x plus 6 is equal to 0. And this is clearly true because you can just plug in if x is equal to 2, then 2 squared minus 5 times 2 plus 6 is equal to 0. Or, like, I have this problem because you can factor out this as x minus 2 and x minus 3. And now this is equal to 0, so this is 0. So if you don't use proof by contrapositive, then this will be harder or more complicated. But if you use contrapositive, it becomes trivial. So sometimes if you see things like something not equal to something implies something not equal to something, or something not like just whenever you see not something implies not something, you always think about the proof by contrapositive. Okay? I think it's enough for this video. I will see you in next video.